Hi, this is Sheikh Hannu. I am pursuing B.Tech second year in VVITU. I am from ECEC department. Today we are going to discuss the main topic in STLD switching theory and logic designs in Unit 1 reviews of number system. In that reviews of number system are divided into two parts. Part A review of number system and codes, and the part B Boolean theorems and logical operations. In that part B Boolean theorems and logical operations, we have one main topic, right? That is basic fundamental logic gates. Basic logic gates. In that we have to see the we know that the seven core logic operations. Seven core logic operations, there are seven primary logic operations, each with a unique function and a truth table. These gates are fundamental components of digital electronics. We know the seven basic logic gates, and the first one is NOT gate. NOT gate is also known as the inverter. The NOT gate has one input and one output. It performs the logical negation, meaning the output is always the opposite of the input. Means if we see look at the through truth table of a NOT gate, here we give the input 0 and the output is 1. Here we give the input is 1, the output is 0. It means the symbolical expression of a NOT gate or inverter is a y equal to x bar. Okay. Okay, we have okay the second logic gate is AND gate. The AND gate takes two or more inputs and produces a single output. The output is only true one if all the inputs are true. Okay, otherwise it's false zero. One indicates true, zero indicates false. Okay, if you see the truth table here, we have the two inputs I1, I2, and the y represented as output. Here we see the truth table. The logical expression of the AND gate is y equal to I1 into I2. It is the basic multiplication. 0 into 0, 0. 0 into 1, 0. 1 into 1, 1. Okay. Okay. The third common logic gate is OR gate. The OR gate produces a true 1 output if at least one of its inputs are true 1. The output is false 0. Here it is also the same condition like a AND gate. Here the true condition means 1, the false condition is 0. If all inputs are false, it is a 0. Okay. Here it is also the two inputs I1 and I2. It, here it have the one output y. The symbolic expression for the OR gate is y equal to I1 plus I2. Here the fourth logic gate is a NAND gate. NAND gate is also known as a universal logic gate. The NAND gate is the inverse of an AND gate. Inverse of an AND gate means it is a opposite of AND gate. Its output is a false 0. If all inputs are true, 1. Otherwise the output is true. Okay. Okay. Okay, see the truth table of I1, I2 are the inputs and y is the output. The logical expression for AND gate is y equal to I1 into I2 whole bar. Okay, and we have seen the fifth logic gate. Fifth logic gate, NOR gate is also known as universal logic gate as well as NAND gate. Okay, the NOR gate is the inverse of an OR gate. Its output is a true 1 only if all inputs are false 0. Otherwise, the output is false 0. Let's see the truth table I1, I2. Similarly, we have to compare from the above logic gates. I1, I2 are the inputs and y is the output. The logical expression for the NOT gate is I1 plus I2 whole bar. Okay. Here we see the another logic gates is XOR gate. XOR gate is also known as the exclusive or OR gate. The XOR gate outputs a true 1 if an output number of inputs are true 1. It's often used for a parity checking. Parity checking. It is the main point, parity checking. See the truth table of I1, I2, and the output is y. The logical expression behind the XOR gate is y equal to I1 XOR I2. It is also simplified in terms of I1 bar into I2 plus I1 into I2 bar. It is also it is also simplified like this. Okay. The last basic logic gate is XNOR gate. XNOR gate is also known as exclusive NOR or even gate. The XNOR gate outputs true 1 if an even number of inputs are true 1 or if all inputs are same. It's the inverse of the XOR gate. The truth table of the XOR gate is here. This is also the two inputs I1, I2, and the one output Y. Okay. The logical expression for XNOR gate is I1 XNOR I2 equal to, it is also simplified in terms of I1 bar into I2 plus I1 into I2 bar whole bar. It is also simplified in terms of I1 bar I2 bar plus I1 I2 I1 I2. Okay. Okay. We have to see the water logical operations. Water logical operations. Mm, water logical operation in terms of manipulating to true or false values, foundation of digital systems, enabling decision making. Okay, first of all, we see the manipulating to or false systems. Logical operations are functions that process and transforms a binary true or false value based on specific rules, forming the core of Boolean theorems. Boolean theorems or Boolean logic. We see the second foundation of digital systems. They are fundamentals to computing, programming and digital electronics, serving as the elementary decisions and circuit making. Okay, okay, it enable, and the third one is enable decision making. By evaluating conditions, these operations allow digital systems to make intelligent choices and control information flow from a simple arithmetic complex AI, artificial intelligence. Okay, if you see the okay, why logical operation matters. Logical operations are the unseen foundation of our digital world, from the simple calculator to the most complex artificial intelligence. Every decision and computing relies on this basic true false building blocks. Okay. Okay, these are the, here we see the three modules. The first one is a digital circuit core, and the second one is a programming language, and the third one is a complex and computations. The computations. First of all, we see the they form the first of all we see the first module, a digital circuit core. They form the bedrock of all digital circuits, including central processing units. It is also known as CPU. It is a memory of the system, memory units, and a networking hardware. And the second module is the programming language, essential in programming for controlling conditions, if else, managing loops and loop condition, implementing intricate decision trees. And the third module is a complex computations. The complex computations enable the execution of highly complex computations by breaking them down into simple true false evaluations, processing vast amounts of information. Okay. If you see the second one, uh, the NOT operation or a negation or inversion. The NOT gate, also known as inverter. We see already on the above slide. It is the simplest logic operation. It takes a single binary input 0 or 1 and flips its value to the opposite state. Okay, okay. If you see the basic foundation, simple and notation, real world analogy. Okay, first of all, we see the basic foundation. Take one output and reverse it value. 0 becomes 1, 1 becomes 0. It is the reversal. Okay, and the second one is a symbol and notation of a NOT gate, represented as you see the symbol. Okay, and the third module is a real world analogy. Real world analogy. If raining is true, if ra- if raining is true, not raining is false. If wet is false, not wet is true. It is the one of the module of real world analogy based on the not operation. Okay. Here we see the truth table, input and output not output of not gate. 0 means false, 1 means true. 1 means true, 0 means false. It is the inverse of the input. Okay. The output is inverse of the input. And we have see, we discussed about the NAND and NOR gate, the universal gates. Here the clear cut explanation about the NAND and NOR gates. it is also known as a universal logic gates. NAND and NOR gates are also known as a universal gates because any other logic gates like AND, OR, NOT, XOR, XNOR can be constructed using only NAND gates or only NOR gates. This makes them incredible versatile and important in a digital circuit. The the name universal logic gate not comes true. Okay. It is the main gates NAND and the NOR. It is a main logic gates. Okay, see the NAND gate and NOR gate. NAND gate performs a NOT AND operation. Output is false only if all inputs are true. Otherwise the output is true. NOR gate performs a NOT or operation. Output is true only if all inputs are false. Otherwise the output is false. Okay. Okay. Okay, see the truth table of NAND gate and the truth table of NOR gate. We have already discussed it from the above slides. Okay, the truth table of AND gate and the OR gate. Here we see the A and B are the inputs are the NAND gate, and similarly A and B are the inputs are the NOR gate, and the NAND gate operation is A into B whole bar, and the NOR gate operation is plus B whole bar. Here we see the another module of visualizing logic gate symbols. Each logic gate has a unique graphical symbol that helps engineering quickly understand the function of a circuit diagram. The symbols are standardized globally, making circuit designs universally readable. Okay, we have the AND gate, OR gate, NOT gate, or inverter, XOR gate, NAND and NOR gate. Okay. If we see another, logic powers the digital world. Hmm? Understanding logic operation is crucial for anyone engaging with the technology as they underpin virtually even digital systems and process. Hmm. Here, here see the three models of first one is a fundamental operation and the second one is the extended capabilities and the third one is a foundation for computing. Here we see the first module matter and OR and NOT gates are the absolute basis forming the core of all digital logic. And the second module matter is XOR, NAND and the NOR gates provided additionally flexibility and power allowing for more complex crucial designs and efficient logic implementations. And the third module is a foundation for computing. Mastering these concepts is a fundamental for the corresponding the architecture functionality of modern computers and electronic devices. Okay. Mm, okay. These are the here we see the clear cut explanation about the basic logic gates of basic logic gates. We know that the NAND and NOR gates are universal logic gates. Here we see the clear cut explanation about the NAND and NOR gates in the part 2 of unit 1. Boolean theorems and the logic designs. Boolean theorem and the logic designs. Okay, thanking you.